Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, so I did a video on GaN, the future of power electronics. And I used this Renaissance board, this evaluation card. It has a gate drive driving a GaN FET. And so, you know, what I want to do is I want to kind of explain, I want to kind of compare the difference of a Mosfet and a GaN, okay? And so let's talk about that a little bit, just so you can see why the GaN is going to replace MOSFET in many applications. All right. So yeah, and by the way, these evaluation cards, they're free of charge. The vendor Renaissance provided that free of charge, and so it's pretty nice. As an engineer, I'm kind of used to getting evaluation cards free, so I guess I just ask them to give them to me. But I tell them what I'm going to use them for, and they decide if that's valuable for them, and so they do. But you know, obviously there's no hooks or anything like that. They just send them to me. And this one I got free because they had a marketing campaign, and you just had to fill in some, personal data, and they chose so many people, and they sent out free ones. So that's how I got that one free. But alright, so what I want to do is I want to just talk about the GaN FET, the gallium nitride FET, and there's a figure of merit that they have with MOSFETs, or FETs, general. And so the GaN figure of merit just looks a lot better than a MOSFET. The two main characteristics they use for the FOM is the RDS on, because when a FET turns on, you want it to be ideally 0 ohms, but there's some internal resistance, so that's the R drain to source on resistance, RDS on. So, and it's in milliohms for the kind of FETs that we normally use in our voltage ranges. And then there's also, you have to turn them on, and so you have to put a voltage on the gate. They're voltage driven devices, not like a bipolar junction transistor that's current driven. You have to put current, and then the gain is going to take that current, multiply it, and give you a collector to emitter current gain. But in a MOSFET, you put a voltage on the gate, and as you increase the voltage, the thing turns on. Okay? And so as you turn it on fast, like in a switching power supply or Class D audio amplifier, you're going to have to charge and discharge that gate, and that's they call that the gate charge. Okay? It has to do with, there's an internally, basically some capacitance from gate to source, capacitance from gate to drain, and you're charging and discharging those things. There's capacitance from drain to source, and you're just charging and discharging those things. And it used to be that, I remember looking at, comparing FETs by looking at the capacitance from gate to source. But that wasn't the only factor. The capacitor from gate to drain played a part in that charging, discharging as well. So they came out with this term, which makes it easier to compare FETs. See how easy it is to turn them on and off. Okay? So that's how they come up with the figure of merit, just kind of combine these two terms, and then you have a number you can compare FETs to within the same voltage range. Or you don't want to compare a FET that has a 600 volt drain to source with, say, a 100 volt FET, because they're going to have different characteristics, so it's not a fair comparison. But anyway, so figure of merit. Okay, now I'm going to show you in the data book, what that looks like and the trade-offs. Okay, and I'm going to show you between a MOSFET and a GaN what that looks like. Okay. Alright, so then there's some other things that come into play. So there's 3 more things I think are important, really 4, these 2 timing things. So what it is TF, time fall, and time rise, TR. Okay, the rise and fall time. And the gate to source, the voltage gate to source threshold, okay? And the time of reverse recovery, okay? So let me just explain that. When you turn on the, okay, let me see if I can draw this here. If the FET is on, okay, and you turn it on, it has a fall time I'm exaggerating this, and then it's on for a while, and then you turn it off and it comes up. Okay, so this time here, this fall time and rise time, it doesn't happen instantly like we'd like it to. So those two things are important factors. The gate to source threshold, what that is let's say that you're putting the voltage in at the gate. Let's say here's our thing. Okay, so let's just say across this axis, we'll call it charge, okay, that Q thing. So as we're putting charge in, then we get current. Okay, so as we do that, we add some charge and the current starts to rise. Okay, this is current. Wow, I'm doing this left-handed. Okay, so as we do this, there's a point where it actually kind of flattens off, and then you have to push it past this barrier, and then you keep on adding, and then it takes off again. Okay, and this is the threshold. So, you know, that could be 2, 3 volts, 1 volt, you know. So you want to just compare that. If you're comparing FETs, you want to pay attention to that. And if you want a FET to turn on early, then that matters, that threshold. Also, this matters. How long that flat period is. How much charge you have to get past before you can start really turning it on, okay? So it's kind of like a garden hose. You start turning it on, then pretty soon it just spins, nothing happens, and all of a sudden it catches again, and then it really starts to turn on as you turn. So, you know, so those things here, gate, these fall times, and then this reverse recovery. All right, what's that? Well, okay, I'll tell you what. If you're switching this transistor on and off, here, let me erase this for quickie, this waveform I drew here. All right, I drew a little circuit here. Try to explain this. Okay, so let's say we have a buck converter. We turn this guy on and allow current to flow through the inductor. So current's flowing through the inductor, ramps up, and it ramps up in the inductor, and then we turn it off. Well, then it's going to start ramping down, but the current has to keep flowing, so it wants to keep coming this way. This guy's turned off, so the current flows through this body diode and the FET. Now, what we like to do is turn this FET on immediately. If we could turn this off instantaneously, turn this on instantaneously, that'd be the ideal thing. But we can't do that because of that fall time, rise time thing. So you have to have a little bit of delay in your control IC. So in between that delay, while we're waiting, we have this body diode that can start conducting current. So as soon as this guy turns off, then this diode starts conducting current to this. Okay? Okay, so then let's just say this FET turns on and it continues to allow that inductor current to drain down. Well, then this guy turns off and the current continues flowing through the diode, but then this guy turns back on and restarts the circuit. Well, when that does, then this diode's going to block that current flow from going this way, right? Well, that's true, but not instantaneously. So there's a reverse recovery time. This diode actually has to have, it actually almost looks like it's short for a moment when this guy turns on, and then the barrier region inside that diode, there's a charge and discharge thing that takes place, and then it separates and turns into an open diode again when you have a positive voltage going this way. But for a moment you get a little bit of shoot through, and that's reverse recovery. So then when this guy turns off, then now all the current's going this way. So what happens is you get a little bit of a dissipation in that transistor because of that diode having to turn itself off. So that's a parameter. When you look at a Mosfet in the data sheet, down under the body diode, you'll see this reverse recovery time as one of the parameters, okay? Okay, in a GaN FET, let's just go through this stuff. RDS on is really low. Sure, I mean, there could be some FETs with RDS on as low, but it's hard to find a FET that has RDS on and gate charge better than a GaN. Not only that, these other parameters are really important because the fall time and rise time are much shorter on a GaN. They turn on and off much quicker because there's a lot less charge in the FET, okay? So then the gate to source threshold, okay, there again, you might be able to find, I'm sure you can find FETs that have thresholds equal to a GaN. But again, it's all these things coupled together. The gate source threshold, this thing here is usually short, this little charge thing, because it doesn't, that's the beauty of them. You can turn them on fast so they don't have a lot of charge, okay? Well, let's just talk about this gate source a little bit. With more powerful FETs, you know, it used to be that you had to have a higher voltage, say 10 volts on the gate, to make sure that it was fully on, that you really had it, you know, that faucet turned all the way on, okay? And FET's gotten better where it doesn't take as much voltage, but when you have to go higher up in voltage, you're charging those caps, you know, capacitors higher up, and then you have to discharge them. And the energy in that is capacitance times voltage squared. So when the voltage goes up just a little bit, it's important because it's squared in the math for the energy, okay? So that's an important thing, this gate source. And like I say, you can find a FET with the same gate source threshold as a GaN, but when you compare the other things, they don't all stack up together, okay? So it's kind of like if you had two football teams playing against each other. You might have one football team that has a great quarterback, but maybe the front line's not as good, you know, so there's trade-offs. With the GaN, most of these parameters combined together are all low. We're all, you know, on the positive side. And then this thing right here, the reverse recovery. Well, in a GaN, the body diode, it's not built the same way as in a Mosfet. In a Mosfet, it's just part of the structure, and so you're stuck with that. And so it's like truly a diode in there. It's PN junction, and again, it has a diode function, but it's really different than a Mosfet. It has to do with the structure of the way the GaN is made. It looks like a body diode in there, but it's not a real PN junction, okay? On the negative side, instead of say 0.8 volts, 0.7 volts that you might find on a body diode in a Mosfet, and again, the diode might be like over a volt, okay? And so it's a higher voltage drop. So that's the negative side. The positive side is that there's no reverse recovery because you're not charging or discharging a PN junction with minority carriers. So it's just a difference in the structures, okay? So anyway, all these things, we're going to look at just some data sheets, and I'll just kind of show you there, and maybe that'll make it a little more clear. Hopefully this helps. And hey, by the way, if you haven't subscribed, do so. Like the video if you like it, and you know, it's always important to hit that like button. And hey, thanks for watching the video and supporting the channel, and especially the Patreons. Thanks a lot. Appreciate that, guys. Alright, so now let's look at the data sheet. Alright, so what we want to do is find some good 100 volt MOSFETs to compare to a GaN 100 volt FET at about, say, 20-16 amps. So I searched for the MOSFET and kind of searched for those terms and ended up with 26 results. So if we come down here, right at the top of the list, we see a couple good candidates. There's this guy here, a part number from Diodes Inc., and this part number from Infineon. This guy in between, this Rome, he's a larger package. These guys are kind of the newer packages, so let's compare those two. And turns out it's a pretty interesting comparison, because when we come over, this guy 20 amps, this guy's 18, pretty darn close. This one's 62 milliohms. Even though it can handle higher current, 62 milliohms. This guy's not quite half, it's 38 milliohms. And then this guy that's 62 milliohms has 4.5 nanocoulombs, where the lower RDS(on) has, you know, almost, well, it's like twice the gate charge, 9.1 nanocoulombs. So right there, if you multiply those two guys together, you get a figure, probably be pretty close to this one. Although they're really different types of FETs. One has better switching, or lower switching losses and more conduction losses, where this one's just flip-flopped. Very interesting. So let's compare that Well, let's pull up a data sheet. Okay, so here's the data sheet for the diode zinc. Zoom in on that. Now look, the interesting thing, you need gate source of 10 volts to get 20 amps and to lower the RDS on to 62 milliohms. Otherwise, at 6 volts, the RDS on goes up to 77 and max current drops to 16 amps. There's nice, interesting small package. Now, right down here, I want to point out January 2019. So really new, updated, latest technology kind of stuff. Okay, so one thing I want to point out right here, so I want to point out this, 3.3 degrees C per watt is the resistance theta from junction to case. Okay, so if the case is, whatever temperature, say 50 degrees C, the junction is going to be 3.3 degrees C for every watt hotter. So if you have 2 watts dissipation, it's going to be 6.6 degrees hotter. So, that's something you can't really do anything about. That's just the resistance of the package. Up here, this is junction to ambient, 61 degrees C. This is based on Note 5, which is 1 inch square of 2 ounce copper FR4 board. That one you can do something about because you can heat sink better. You can try to lower that number, but this number is just to do with the package. Okay, we come down here. Here's the RDS on numbers, and here's the QG, the 4.5 nanocoulombs, and that's for the gate voltage of 10 volts. Here's some time delays and the time rise and fall that I was talking about, the rise and fall, but I kind of left off. There's a delayed time too for on and delayed time for off. So you can see these times. Now here's the reverse recovery time that we talked about, 22.9 nanoseconds, where GaN won't have any of that, it's 0. And here's a charge. It actually has a charge at 45.2 nanocoulombs. So that's how you can kind of calculate how much energy you'll dissipate depending on your switching frequency. Okay, and here's a curve I thought interesting, the gate source voltage versus the gate charge. Now, see this right here? What you'd like ideally is just a linear line, but you have this step here. So between 0.5 nanocoulomb to 2 nanocoulombs, it's kind of flat. So when you drive this thing, you drive it hard to try to shoot through that region. But that's just something important. That's around 3 volts, it looks like. Safe operating area, this curve right here, very important. Shows 100 volts. It's only rated 100 volts, so you can't go above. So it's safe to be 100 volts and less. That's what that means. And up here, it goes all the way up to 80 amps. But this is at 1 microsecond. This next line is 100 microseconds and so on. So for pulses, you can get up some pretty high currents. But then look at this dash line. This has to do with the RDS on. And I can tell you this drops down to 0.8 amps for 0.1 volts across drain to source. So if you're using this as, like, say, a switch, then you only want to put about less than an amp through it if you got 0.1 volt. Now, if you can't turn it, so you really want to turn the gate on hard to get it down, to drop that voltage down. But you're kind of limited on the continuous current. Now it's a small package, so now I can tell you the GaN FET we're going to look at, it's going to be even a smaller package, but it'll come up here around 3 amps. It'll come up here and it'll be flat and then drop down 100 microseconds. And this part looks about the same, but the RDS on portion is going to look better. So let's come down and look at the package. Now here's the package. You can see this metal slug here that sits on the board that gets soldered down. But right here, D, that's this dimension across here, and E, that's the dimension on this side. So come over here to capital D, it's 3.4 millimeter. E is 3.4 millimeter. So 3.4 by 3.4 millimeter. Okay, let's compare that to this GaN FET. Here's an EPC 2016C, 100 volts, 16 milliohm, 18 amps. So you can see it's a smaller RDS on. Now, we're going to just jump down. You can see some of the specs. Oh, here's a temperature one. The junction to case is only 2, so it's at least 50% better. because the case is so small, it can get the heat out faster. So that's a nice thing. Here's the gate. Total gate charge is 4.5 nanocoulombs. So it's the same as that FET, but the RDS(on) is much lower. So the figure of merit is going to be better. All right, now here's the gate charge curve. And you can see the flat part goes from 1 to 1.5. So it's quite a bit shorter. It's at least half as short, this flat spot, as the Mosfet. So it's got a little bit more of an ideal curve here. And the max is 3.5 nanocoulombs here. Okay, safe operating area. So like say it starts off at 3. The dash line comes up. And it's about the same point, 80 amps. And then it comes over here and drops down. So that's 100 microsecond line right there. So yeah, that looks better too. Let's look at the package. Okay, here's the package, and this A dimension right here and B dimension are the two sides. And this is a micrometer, so if you put a decimal point 3 spots over, it'll be 2.1 roughly by 1.6. Here's the drain, source, and substrate. Okay, here's the package up here. That's kind of a photograph of it. And there's the 2.1 by 1.6. So this guy's quite a bit smaller. And here's applications: high-speed DC-DC converters, Class D audio amp. Okay, let's go look at just a sheet of paper that I'll just write these numbers side by side so see them at a quick glance next to each other. All right, guys, so here is a summary. Now, first of all, the size. This is a Mosfet up here, and this is a GaN. I guess I should have did that, but so the Mosfet's 3.4 by 3.4 millimeters, and the GaN is 2.1 by 1.6 millimeters. So that's about a third of the size of that one as far as area on the board. Okay, so this guy, the Mosfet, is rated at 20 amps if you have a gate source of 10 volts, 16 amps with gate source of 6 volts. The GaN is 18 amps at a gate source of 5 volts, so it takes less voltage. RDS(on), at this voltage, 10 volts, you get 62 milliohms. At 6 volts, 77. And the GaN is 16 milliohms. The gate charge is the same, 4.5 nanocoulombs for both. And the thermal resistance on the Mosfet is 3.3 in that package. And in this little package, it's only 2. So it can transfer heat quicker or easier. Okay, that was just a quick summary, and I hope that helps kind of explain the figure of merit. Hey guys, I hope that helped, kind of give you a little bit better look at the difference between a Mosfet and a GaN. There's a lot more stuff to look into. I mean, it really gets kind of detailed. But I just wanted to give kind of the bird's eye view of the differences between them and why the GaNs look so much better. Negative side of the GaN, they do take you don't have to have a drive chip with them, but the drive on the gate, you just have to be very sensitive that you don't go over the voltage, like say 6 volts on them, or you'll kill them. Okay, so you just want to be very careful, and if you are switching them on really fast and turning them off real fast, you're going high frequency with what they're made to do, then inductance, parasitics can be important. So those gate drive chips just make it a whole lot easier to do. All right, and even with the gate drive chip, the size comparison is, looks great. Okay, just want to explain that. So I hope that data sheet made sense. Hey guys, and by the way, subscribe if you haven't done so. Like the channel or like the video. That helps me. And I've got links below for other things, Patreon links and that. Thanks, Patreons. Thanks everybody for watching. And I hope this, was just kind of a quick overview, but I hope this helped kind of explain the difference between GaN and Mosfets. Okay? Alright, thanks guys. See you next time.